Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to discuss how to update a probabilistic model when the values of some of the variables are revealed. This will lead us to define the conditional distribution of discrete random variables given the values of other random variables, and also to discuss independence and conditional independence for random variables. Let's get to it. We're going to discuss in particular conditional distributions of discrete random variables. Again, our motivation is this question: how do we update a model if the value of some of the variables within the model is revealed? Remember that the way we describe the joint distribution of multiple random variables, multiple discrete random variables, is through their joint probability mass function. The joint probability mass function tells us the probability that the random variables take certain values at the same time. Here we have two random variables, A and B, that can take 3 values each, and the joint PMF tells us, for example, the probability that A is equal to 1 and B is equal to 3 at the same time. This probability is 0.4. However, imagine that the value of A is revealed and it happens to be 3. How do we update our uncertainty about B? Well, if A happens to be 3, now we know that we're in this part of the joint PMF, if you want, where A is 3 and B is equal to any of its possible values. We know that this has not happened, A was not 1, and this has not happened, A was not 2. So it's rather natural to take these probabilities and use them to update our uncertainty about B. Remember that when we were computing marginal random variables, we were doing something very different. We were aggregating. So if we want to compute the marginal of A given B, what we were doing is we were summing in this direction. Okay, we're summing these guys to get the marginal. Now what we're saying is we actually know that A is equal to 3, so we're discarding part of the joint PMF and we're just keeping the part that is relevant, the part that is that corresponds to the value that we have observed. Of course, if we just take those values, this is not going to be a valid PMF. It's definitely non-negative, but it doesn't add up to 1 because the whole joint PMF adds up to 1 and we have thrown part of it into the trash, right? So we need to normalize these values in order to obtain a valid conditional probabilities. Let's do this a bit more mathematically. We define the conditional probability mass function of B given A as the conditional probability that B takes any of its possible values given that the value of A is fixed. So this would be 3 in our example. By definition, this conditional probability is the probability of the intersection between these two events, A being equal to this value and B being equal to that value, divided by the probability of the event that we're conditioning on. Now, if we plug in the definition of joint PMF and also marginal PMF here, we see that the conditional PMF of B given A is just equal to the joint PMF divided by the marginal. Here, it's very important for you to pay attention to the role of both variables. So here, A is fixed. In our example, A was fixed to 3. So here, A is also fixed. And here it's also fixed. In fact, this is just this term that we needed to normalize the probabilities when we took this slice of the joint PMF. Now we have to normalize this. How are we going to normalize it? Dividing by the sum. But what is the sum? The sum is exactly the probability that A is equal to 3. Remember from how we compute marginal probabilities. So this term here is doing exactly that. It's just normalizing. This other variable, on the other hand, B, is the variable over which we're computing probabilities. Okay, there seems to be a little bit of a delay when I write on the slides. I'm sorry about that. That's the value over which we compute probabilities. It's very important to make that distinction. You can see that values to the left of this conditioning line are the ones where we're saying, oh, the probability that B is equal to this value is whatever, conditioned on this other stuff. the values on the right of that conditioning line just index those probabilities. That's what we're conditioning on. Okay? So here, once we normalize dividing by the probability of A equal being to 3, we get this valid conditional PMF. Here I'm showing you the PMF for A equals 3. If we changed A to something else, we would obtain a completely different PMF. However, or maybe not however, I don't know why I said however there. Then there's the other variable B, and that just tells us, the values over which we're computing the probabilities. It's very important to make this distinction when you're visualizing a conditional PMF, because at the end of the day, when you see it written down, it's very easy to confuse. All right, so the conditional PMF is a valid PMF. It's non-negative. It contains conditional probabilities, so they're all non-negative. And it adds up to 1. Let's check that that is indeed the case. First, we need to think it adds up to 1 over what? Well, over the variable over which we're computing probabilities, right? So we're going to sum this conditional PMF over all the possible values of B, not of A. That wouldn't make sense because A is just this index that tells us which of the conditional PMFs we're getting. So here when we sum this, we get the sum of the joint PMF divided by the probability, the marginal of A at that value. And when we compute this sum of the joint PMF, this is just the marginal of A at A. As I said, this slice that we were talking about, if you sum all of those probabilities, it's just the probability of A. So indeed, this term normalizes the conditional PMF so that it adds up to 1. Again, I really want to emphasize that it makes sense to do something like that, to sum the probabilities over B, but it makes absolutely no sense to sum them over A. You always need to remember that this parameter A here that we have in the conditional PMF just tells us which of the conditional PMFs we are getting. It's not a variable over which we compute probabilities. We don't say the probability of A. It's the probability of B conditioned on A having that value. Okay, hopefully that makes sense. So in particular, if you try to sum this conditional PMF over A, I have no idea what you're going to get because it doesn't make sense to do that. All right, so let's take a look at an example. Here, if you remember from the video on multivariate discrete random variables, we have ratings for 2 movies that came out in 1996, and I'm so old that I saw at the cinema. They're Independence Day and Mission Impossible. This is the joint PMF. So for example, this means that 5.7% of the people gave a 3 to Independence Day and a 2 to Mission Impossible. So what if we're interested in the probability that, not the probability, the distribution of Independence Day, given that Mission Impossible got a rating of 1? Well, what we're going to do is we're going to take that slice of the joint PMF and we're going to normalize it just as we did in our other example. And when we do that, this is what we obtain. Now let's think a little bit about what these conditional PMFs actually mean. We're going to compare them to the marginal. So remember that the marginal was obtained by summing over the rows to just isolate the behavior of the random variable Independence Day on its own, and this is what we get. So this is if we don't know anything else about the user, how do people like Independence Day? Now what we're doing is we're conditioning on the fact that they didn't like Mission Impossible in this case. It seems that those people tend to not like Independence Day either. Then, they disliked Mission Impossible, they didn't dislike it so much. Those people tend to like Independence Day a little bit more. And as we move to liking Mission Impossible more and more, we see that there's a clear dependence, a very strong dependence between liking Mission Impossible and liking Independence Day. The people that loved Mission Impossible also love Independence Day. So the conditional PMF is capturing this relationship, this dependence between the two quantities. Now we can also consider the conditional joint PMF of several variables. So here we have a model where there's 4 quantities encoded as a 4-dimensional random vector, and 2 of them are revealed. So the first entry and the fourth entry are revealed to be equal to A and D respectively. So how do we update our uncertainty about the second and third entry? Well, we basically freeze the values that we're conditioning on. Okay, we freeze these guys, and then we consider the joint PMF over the rest. Okay, this is going to be the conditional probability that the second entry is equal to B, the third entry is equal to C, given those frozen values. By definition, that is equal to the probability of the random vector taking all of these values divided by what we're conditioning on. Okay, seen otherwise, which is a little bit how I was explaining it, we're freezing these values within, this is what I meant by this freezing business. We're freezing the first entry and the fourth entry, and we're only considering the distribution over B and C, but we have to normalize so that this thing actually adds up to 1 if we sum it over B and C. How do we achieve that? By dividing by the sum, which is just the probability that the first entry is equal to A and the fourth entry is equal to D. Okay. Hopefully that makes sense. In general, what do? We put the joint PMF, we fix the values that we're conditioning on, and then we have to divide by the joint marginal PMF of those values so that things are normalized. By definition of conditional PMF, we get a chain rule for discrete random variables. Because the conditional PMF is equal to the joint divided by the marginal, we can, put the marginal on the other side, and we get that the joint is equal to the marginal times the conditional. This really looks very similar to the chain rule for events, right? We can do this in both directions. There's nothing special about the order AB. We can also take out B first and multiply its marginal by the conditional to get the joint. This type of factorizations we do all over the place in probabilistic model and in homework problems, and it's very important to choose the order. Even more important when you have many random variables, because what we just said holds also for the random variables that we can stack in a random vector. So here the idea is exactly the same. We can factorize the joint PMF of a vector that has the entries as the product of the marginal of the first entry, and then we have to condition on everything that we have taken out, just as we did for events. Okay, so just to be clear, this would be first we take the first entry out, equal to whatever this deterministic value is equal to, the first entry of that. Now we take the second entry, and we have to condition on the first one, and so on and so forth. Okay, I'll do the third one. While I do the third one, I will say that, of course, we have to now condition on x1 and x2, and this follows immediately from the definition of the conditional PMF. You just have to do it in 2 steps. This is just like when we discussed the chain rule for several events. Okay, and here we put remember that here in the notation, these guys are all deterministic fixed values, and the squiggly lines indicates random variables, in case you're getting confused by that. All right, and now we put those there, and we would continue and so on and so on, and you always need to condition on whatever you've taken out first. And here, as you can see, it gets very messy, and I have taken out first the first entry, then the second entry, and so on. You could do this in any order, but it's very important to choose the order when you're doing probabilistic models, probabilistic modeling or homework problems. Okay, any order works, and choosing the order wisely is actually very important. All right, let's take a look at an example where we have 3 random variables. We're going to model the precipitation in these 3 weather stations in Oregon. We already saw this example in the video on multivariate random variables. We just represent precipitation as either 1 or 0. If it rains in Corvallis, then we get a 1 in Corvallis. And these are hourly measurements from 2015. So we derived this joint PMF that tells us, for example, that the probability that it's not raining in any of these three places is around 83%. The probability that it's raining in all of them is very, very small, 0.8%. All right, so now what if we want to compute the probability, the conditional probability of Corvallis and Coos Bay, conditioned on the fact that John Bay is equal to 0. So we're saying that we know that this has happened. So what do? Well, basically, we discard this because we know it has not happened. We get that slice of the joint PMF. Now we have to normalize it so that it adds up to 1. How are we going to normalize it? By the sum of these guys. But what are the sum of those guys? They're just the probability that John Day is equal to 0. Okay, so this is just to show you that our formula for the conditional PMF stems essentially from common sense. And this is the value that we would get for the conditional joint PMF of Corvallis and Coos Bay, given that it's not raining in John Day. Here we're comparing it to the marginal, which is obtained in a very different way. In the marginal, we sum over John Day. Okay, we're not fixing a value for John Day. It's important to remember this distinction. What if we want the probability conditioned on John Day being equal to 1? We do exactly the same thing. Okay, we preserve these guys because John Day is equal to 1. And these other guys go to the trash. And we normalize. And from here you can see that these conditional PMFs can be extremely different. And in fact, it's really different, right? When it's raining in John Day, there's a clear dependence between precipitation in these places. We see that the probability of it raining in Coos Bay and Corvallis goes up. It's always good when you've computed a conditional PMF to take a look at it and see if what you see makes sense, and of course compare it to the marginal. What if we know that it's not raining in Corvallis and it's also not raining in John Day? So now there's only, so it's not raining in Corvallis and it's not raining in John Day. We preserve this. It's not raining in Corvallis, it's not raining in John Day. We preserve this, and the rest goes to the trash. So now we're going to get a PMF, a conditional PMF of Coos Bay, given that it's not raining in the two other places. We need to normalize this. What do we normalize by? By the sum of these two probabilities, which is exactly the probability that Corvallis is equal to 0 and John Day is equal to 0. All right, now we're going to look at that conditional PMF for different possibilities. This is the marginal. This is if you sum over Corvallis and John Day. Now we're not summing, we're fixing values. Here we see what happens when it doesn't rain in either of the two other places. If it rains in John Day, if it rains in Corvallis, you see that if it rains in Corvallis, it makes a huge difference. We'll talk a little bit more about this in a moment. And if it rains on both of the other places. Okay, so the conditional PMFs tell you the relationship between precipitation in these three places. Let's do one last one. What if you want, and this one is a little bit tricky, so I would suggest maybe you pause the video and you try to figure this one out on your own. How do we compute the conditional PMF of Coos Bay given only Corvallis is equal to 0? Okay, so maybe pause the video and think about it. Hopefully you've done that. If not, that's completely fine. We're all adults here. Okay, we want to condition on this, right? So we're going to discard this part. We know this did not happen. But now we're not interested in also conditioning on John Day. So what do? We aggregate these probabilities. We sum over John Day here. And that's how we get the conditional PMF of Coos Bay given Corvallis. Then we have to actually normalize these guys by their sum, which is going to be the probability that Corvallis is equal to 0. Okay, so hopefully that makes sense. And now we're going to see the marginal that we get. This if Corvallis is equal to 0, Corvallis is equal to 1. We can do the same thing for John Day. This is the precipitation in Coos Bay, okay? Conditional PMFs of the precipitation in Coos Bay. This is if it does not rain in John Day, and if it rains in John Day, okay? Again, you see that maybe there's more dependence with Corvallis than with John Day, but there's definitely dependence with John Day when we compare to the margin. Let's take a look at two other weather stations. One that is in Hawaii and another one that is in Rhode Island. And before we look at this, how do you think the marginals are going to compare to the conditional PMFs in this case? Just think about it on your own. So this is the marginal for the precipitation in Hawaii. And this is the conditional when it does not rain in Rhode Island. And this is the conditional when it does rain in Rhode Island. So they're pretty much identical. Okay, they're not exactly identical, interestingly. I'm not an expert in global weather, but there seems to be a tiny systematic difference. But at least visually they look really, really similar. Again, we're doing the same thing for Rhode Island. This is the marginal in Rhode Island, precipitation in Rhode Island. What happens if it does not rain in Hawaii? Doesn't seem to affect much. If it rains in Hawaii, also doesn't seem to affect much. So here we have arrived at the concept of independence between two random variables. If the marginals are exactly the same as all the possible conditionals, then we say that the two random variables are independent. Okay, and the intuition is that our uncertainty about one of the random variables, for example, precipitation in Rhode Island, does not change if someone tells us the value of this other random variable, precipitation in Hawaii. How do we capture this? We go back to independence between events, and we remember that for independence between events, two events are independent if the conditional probabilities are the same as the probabilities. Equivalently, if the probability of the intersection factors into the product of the individual probabilities, this is by the chain rule. Essentially the same thing for random variables, which comes from the fact that if we look at events of the form, the first random variable is equal to some value conditioned on the second random variable being equal to another value, if those conditionals are always equal to just the probability that the first random variable is equal to that value, then these two quantities are clearly independent, and we can encode this through the conditional PMF being equal to the marginal PMF for all possible values. Equivalently, by the chain rule, this means that the joint PMF factors into the product of the two marginal PMFs. Usually we would have one conditional here, but the conditional is the same as the marginal. So this captures independence for random variables. This has to hold for all possible values of A and B. Similarly, when we have D entries of a random vector, if we want the random variables to be mutually independent, then we need the joint PMF to factor into the product of the marginals. So here we would have many conditionals by the chain rule. If there's independence, no conditionals, they're all equal to the marginals. If this holds for all possible values of the entries of the random vector, we say that the entries are mutually independent. Let's go back to our example with Coos Bay and John Day and Corvallis. This is the marginal PMF of precipitation in Coos Bay. Let's take a look at how it compares to the conditionals when it does not rain in John Day. It doesn't seem to change very much, and when it rains in John Day, it actually changes quite a bit. So clearly here we do not have independence. Okay? The precipitations in these two places are clearly dependent. Now let's see what happens if we condition on Corvallis. So here we're only conditioning on Corvallis. Corvallis not raining. Okay, this is how the precipitation in Coos Bay looks like, and we've seen that, by the way, Coos Bay and Corvallis are very dependent. Okay, so now apart from conditioning on Corvallis, we're also conditioning on John Day, and here we see that there's barely any difference. And if we condition on John Day, on it raining in John Day, there is a little difference, but the difference is much smaller than when we're just conditioning on John Day raining. So it seems that once we condition on Corvallis, once we know what's going on in Corvallis, the information from John Day is less relevant. It changes the distribution of Coos Bay much less. Sorry for the siren. I don't know if you'll be able to hear it, but this is New York City. What are we gonna do? Okay, so hopefully you see that while we hear the siren. The point is that once we condition on Corvallis, the influence of John Day decreases quite a bit. Here we were conditioning on it not raining in Corvallis. Let's see what happens when there is precipitation in Corvallis. I guess the ambulance or the firemen are coming really close. but I think they're gone now. Again, sorry about that. So now what's up if there's precipitation in Corvallis? So obviously the precipitation in Coos Bay changes a lot. This is a conditional PMF of Coos Bay just given Corvallis. Now let's see if we additionally condition on John Day. So no rain in John Day, barely changes. If it rains in John Day, it changes a little bit. So again, once we know about Corvallis, John Day gives us much less information about what's going on with the precipitation in Coos Bay. And if we take this to the extreme where these guys would be exactly the same as this guy, okay, and the same for these guys, if these guys were exactly the same as this guy, then we would say that Coos Bay and John Day are conditionally independent given Corvallis, because once we know Corvallis, John Day no longer affects the distribution of Coos Bay. The conditional distributions are all exactly the same if and only if we condition on Corvallis. That's the concept of conditional independence. Okay, it kind of makes sense in this case because Corvallis is in between Coos Bay and John Day. So if we know what's going on here, then what's going on here is, not that important. It's actually not giving us that much information about whether it's going to rain or snow here or not. Again, taken to the extreme, of course, this is not completely true for our data set. We had discussed already conditional independence for events. It's really similar to independence. The conditionals are the same, but we always condition on this other event. And we saw that conditional independence is very different from independence. It does not imply independence, and independence does not imply conditional independence. Equivalently, we have that the conditional of the intersection conditioned on that event is equal to the product of the two conditionals. Okay, if this happens, we have conditional independence between the events A and B given C. Very important, and we saw this in the video on conditional independence. Conditional independence does not imply independence or vice versa. When we extend this to random variables, what we say when we say that A and B are conditionally independent given a third random variable, that means that knowing some information about B does not change our uncertainty about A as long as we also know C. So in our example, we need to know Corvallis. If we don't know Corvallis, then Coos Bay and John Day are definitely very dependent. Okay, so this is very important. It's only as long as this other random variable is known. This is captured by the conditional PMFs. The joint conditional factors into the product of the individual conditionals, always conditioning on this third random variable. That's very important. Okay. And this assumption, before we say what we have learned, this assumption of conditional independence is used all over the place in probabilistic modeling, as we will see, because of the curse of dimensionality, even when it doesn't really hold, as in our weather dataset. So what have we learned? We have learned how to compute conditional PMFs. We have learned the definition of independence and the definition of conditional independence. Thank you very much.